Chapter 17 and 18 are both about geology, so I'll lump them together for the lecture. Also, instead of separate quizzes for these two chapters, there would just be one single longer quiz. In my opinion, the strength of geology as a science is that it involves examination of info at a range of scales. You just watched a short video on a nuée ardente, which is a superheated cloud of gas and ash that can be created during volcanic eruptions. Now, the one in the video you watched was actually a pretty slow one. They can move downhill at as much as 500 miles per hour. However, most volcanic eruptions are caused by the sections of the outermost layer of the Earth moving at about 2 inches per year. The devastating 2010 earthquake in Haiti involved only 35 seconds of shaking, while the duration of groundwater flow is commonly measured in tens of thousands of years, and mountain building events take tens of millions of years. Those mountain building events occur over areas spanning thousands of miles, but geologists also study chemical changes that occur at the atomic scale. For an environmental scientist, there are a couple important aspects here. First is how studies at different scales can be integrated. For example, it's not enough to say that the chemistry of a rock has changed. It's more important to discuss the rate of that change and the implications of that geochemical change. Does it tell us the global temperature during that change? Maybe it's related to the use of fertilizers locally. Next, geologists have to make their studies applicable. That's where the principle of a uniformitarianism comes in. This means that the natural laws applicable today were also in effect at earlier times in the Earth's history. In other words, the present is the key to the past, but it also works in the other direction. Lessons from the geologic past can teach us about modern and future environmental changes. The major theme for this lecture is plate tectonics. This is because tectonic activity is ultimately the driver of most geologic hazards and natural resources. And we'll start with just a couple natural hazards: volcanoes and earthquakes. Volcanoes mainly occur near the edges of the boundaries of tectonic plates. You've probably heard of the Ring of Fire that circles the Pacific Ocean. The same does not happen in the Atlantic because the edges of the continents do not match with the edges of the tectonic plates. Instead, the plate boundary is in the middle of the Atlantic, and as a result, the Atlantic Ocean volcanoes stretch from Iceland down the Mid-Atlantic Ridge. On Blackboard, there is a link to a virtual volcano. By altering the composition and temperature of the magma, you can see how the type of volcano and the type of eruptions change. Volcanic activity includes earthquakes, but earthquakes can happen without an eruption. Although tectonic plates move very slowly, in some places, instead of moving continuously, stress will build up. Eventually, that stress can be released suddenly as rocks break and move along a fault line. Typically, this earthquake movement overcompensates for that stress, and so there are aftershocks, which might be seconds or months later, that move rocks back in the opposite direction. There are multiple ways to evaluate earthquakes. Most people have heard of the Richter scale, which is a type of magnitude. Magnitude refers to the strength of an earthquake. Magnitude scales are continuous, and there is no minimum or maximum value. Intensity refers to the amount of damage to human structures as measured on an arbitrary scale. Intensity scales allow the impact, not the strength, but the impact of earthquakes to be easily summarized and communicated. For example, a 3.0 magnitude earthquake in Chicago makes headlines in newspapers, but even a magnitude 5 earthquake in northern Alaska gets no publicity in the press. The difference is that the magnitude of an earthquake does not correlate immediately to the intensity of the earthquake. Okay? The intensity is measuring damage to human structures. The most common intensity scale is the modified Mercalli scale, which is expressed in Roman numerals from 1 to 12. A 1 is essentially too small for people to notice, while a 12 has the ground moving like an ocean wave. The really morbid side of me would actually like to see an intensity 12 quake. Cracks open up in the ground, and where you don't see fractures, the ground undulates like ocean waves, like water. Now on this slide there are some approximate equivalents on the Richter magnitude scale, but keep in mind there is no consistent correlation between the two scales. In addition to the presence or absence of human structures, it's the type of underlying rocks and sediment that will also have a huge impact on the amount of damage, which is measured by intensity. In spite of the fact that people are typically only familiar with the Richter scale for measuring earthquakes, that scale is almost never used by geologists today. The Richter scale was designed for use only in Southern California, and it works well for shallow earthquakes that are near the recording station and are of moderate strength. Instead, nearly all magnitude numbers you will ever see are on the moment magnitude scale, which includes multiple measurements and field observations as well. The actual numbers on the two scales are essentially the same, but moment magnitude numbers are applicable anywhere and are more consistent for strong quakes. Now here's an example on the screen of an old school style of seismograph, a machine that records the Earth's vibrations. These often occur with 3 sensors at each side, one to measure each of the 3 spatial dimensions. Modern seismographs are digital and no longer have these pretty squiggly lines. The height of those lines are important because that's the basis of the magnitude scales. Both the Richter and moment magnitude scales are logarithmic scales. The numbers match the height of the vibration produced by the seismograph, the height of that squiggly line. So each increase of 1 on these scales means the height of that squiggly line increases by a factor of 10. If you compare the seismograms, those printed copies with the lines on it, from a magnitude 5 and a magnitude 7 earthquake, the height of the latter is 100 times greater. Now please note that your book has this wrong, because the textbook says the amount of energy increases by a factor of 10 with each increase of 1 on the scale. It's the height of the seismogram that increases by 10. The energy increase is actually about 32. So the energy of a magnitude 7 earthquake is 32 times 32, or over 1,000 times more energy than in a magnitude 5 earthquake. In other words, a small increase in magnitude means a big increase in the amount of energy being released. So where are the largest earthquakes? Within this learning module, there's a link to a United States Geological Survey page where you can explore the earthquakes within the past 7 days. In some cases, the problems caused by earthquakes are made worse by poorly constructed buildings, as was the case here in that 2010 Haiti earthquake. In more affluent areas, the biggest hazard could be fires started by ruptured gas lines. The highest number of casualties usually result from earthquake-initiated landslides or tsunamis. Such a landslide, a devastating landslide, about 450 years ago in the mountainous part of central China, killed over 800,000 people within a few minutes. Tsunamis are a concern in the coastal areas. Tsunamis occur when an earthquake or a landslide occurs underwater and starts a massive wave of water radiating out in all directions. In deep water, the tsunami waves travel at about 600 miles per hour, but the waves are less than a foot high. The global average wave height from wind is almost 6 feet, so the tsunami passes unnoticed under boats. As the wave approaches shore, the energy that was moving the wave horizontally forces the water vertical. As the water hits the coast, it is usually moving at about 50 miles per hour. The first indication is a sudden drop in sea level, which is followed by a series of tall waves. When we look at the height of some of these waves, we can see that the 1983 tsunami waves that hit Japan were 31 meters, or about 100 feet. These tsunami waves can simply wipe away entire areas. The 2004 Indonesian tsunami's impact was the most devastating in the region of Banda, Aceh. These before and after photos are sobering. The earthquake that caused this tsunami was the third strongest ever, with 4.3 exajoules of energy released. That's almost exactly the same as the annual electricity use for the entire state of Illinois. The strongest earthquake was a 9.5 magnitude event in Chile that had fewer than 1% of this number of fatalities. However, that Chilean event caused a tsunami that was responsible for hundreds of fatalities, as far away as Hawaii, the Philippines, and Japan. So earthquakes are solid evidence that the ground moves, at least a little bit. However, even hundreds of years ago, people hypothesized that land moved on a very large scale. Even relatively early maps of the Americas showed a close match between the coastlines on the east and west edges of the Atlantic Ocean. However, it's not a perfect match for several reasons. For example, in the time since the continents were together, there has been erosion of rock and creation of new rock. It was a German meteorologist, Alfred Wagner, who formalized thoughts on the motion of land masses into the hypothesis of continental drift. Wagner further postulated that all land mass was together, as his diagram in the lower right indicates. It's actually pretty close to our modern reconstruction, shown in that larger image. The most significant difference is that we now think that a large portion of East Asia was not part of Pangaea. Now, in addition to the shape of the coastlines, there were three other categories of data that Wagner used to support his hypothesis. Mountains and rock formations that end on the east coast of the Americas match up to the same features in Europe and Africa. So the Appalachian Mountains are continuous mountains in the British Isles and the Caledonian Mountains, and there are multiple cases of this occurring in North and South America. There is paleoclimate evidence from the past presence of glaciers. Large ice sheets, such as on Antarctica today, move away from the central point of ice accumulation, leaving deep scratches in the rock. Now, initially, geologists were confused by the pattern of these scratches in South America, and Africa, and India, and Australia, until they rearranged the continents the way they would have appeared during Pangaea. If the continents were all together, all the scratches could be explained by a single mass of ice. Finally, Wagner used the distribution of fossils. The green areas are where fossils of the freshwater Mesosaurus can be found. And this is just one of thousands of species of fossils with distributions that can be explained by continental drift. Now, because continental drift explained lots of observations, it was quickly accepted by some. However, most scientists didn't buy it. The biggest criticism was a lack of mechanism. How do you move a continent? Can you feel it moving right now? But because continental drift did explain so much data, research continued. The next insights to evaluating continental drift occurred in the 1950s and 60s, primarily due to work by the U.S. Navy. This was mainly because of the expanding use of submarines. They wanted to know what they might be bumping into. This exploration led to the hypothesis of seafloor spreading at mid-ocean ridges. The initial evidence was the age of the rocks in the Atlantic Ocean. Near the coast, the rocks are about 150 million years old, whether you're looking offshore of Europe or Africa or South America or North America. The rocks become progressively younger as you move toward the mid-Atlantic ridge. And the same pattern has been found at every other oceanic ridge. So that suggests the rock is being recycled someplace and new rock is being created at the mid-ocean ridges and then pushed away from the mid-ocean ridges. Now, the particular portion of the initial hypothesis that dealt with the extraction of rock was basically a guess. So what they knew was new rock was being created at mid-ocean ridges. However, in some places like the Atlantic Ocean, the destruction of rocks at deep ocean trenches doesn't work. But I should say it doesn't work yet. At some point in the future, there will be a deep ocean trench in the Atlantic Ocean, and that's where rock will be destroyed. After the idea of seafloor spreading was proposed, supporting evidence came from the magnetic character of the rock. If you'd use a magnetic compass, you've seen the needle rotate and point toward the magnetic North Pole. But the needle also wants to move vertically to line up with the Earth's magnetic field. The only time when the needle is horizontal with the ground surface, I should say the only time the needle wants to be horizontal with the ground surface, is when the compass is at the magnetic equator. As you move closer to the North Pole, the needle tries to point more and more straight down. At the South Pole, at the exact South Pole, that needle wants to point straight up. So as magma erupts, small crystals within that magma can be rotated and lined up with the magnetic field. As the magma cools and hardens, it locks those crystals into place. It locks that magnetic signature into place where we can read it later. The magnetic field of the Earth reverses periodically, and these changes are captured within the rocks. We can then examine the rocks to determine the direction in which the magnetic crystals are pointing. By dragging equipment across the Mid-Atlantic Ridge, the pattern of magnetic reversals was found to be mirror images on either side of the ridge. That means that not only is new rock being created there, but rock is being pushed to both sides. So far, everything we've discussed is consistent with another idea, the expanding Earth hypothesis. Yes, this idea literally does mean that the size of the planet has increased substantially after formation. Now, hopefully it seems unlikely, but you shouldn't consider it completely impossible. For example, the Earth is accumulating cosmic dust at the surface at a rate that we can measure. There are two other possibilities that are intriguing. I say intriguing, not necessarily believable. Maybe the friction resulting from matter being rubbed together by the force of gravity could cause the interior of the planet to warm and therefore expand. Gravity is a continuous force, therefore the temperature and therefore the size could continue to rise. Finally, at least one variant of the Big Bang theory is that new matter is being created everywhere in the universe to keep the overall density the same. Now, if these particles are preferentially accumulated within the Earth, perhaps because of the density at the center of the planet, well, maybe this world is expanding. Okay, there's only a handful of people who don't find the expanding Earth hypothesis at least a little silly. But continental drift wasn't always accepted either. The problem with accepting continental drift was that it didn't seem realistic that large portions of the planet's crust could move. Likewise, it's the mechanism that is the most serious criticism of the expanding Earth idea. Now, I wanted to have a relatively recent article on here so you can see that the idea is still alive. There are still a few people who claim to support the expanding Earth hypothesis. However, there's a lot more data that support plate tectonics over the expanding Earth hypothesis. Most of this comes from the study of earthquake waves or seismic waves. It's also through seismic waves that we know essentially anything about the interior structure of the Earth. There are three main categories of seismic waves. P waves and S waves both travel through the interior of the body or the body of the Earth. P waves are the fastest, and they can travel through any material. S waves are slower and only travel through solids. Surface waves include multiple complex types and only move along the surface of the Earth. Surface waves are the slowest type of waves, but they do the most damage during an earthquake. Although P waves are the fastest, they do the least damage. So most of what we know about seismic waves is from a global network of recording stations set up around 1960. This network was a product of the Cold War and was developed to monitor nuclear tests. An earthquake results when two rock bodies slide each other in a shearing motion. Therefore, earthquakes produce much stronger S waves, which are the shearing waves, than P waves do. Explosions produce compressional forces almost exclusively, Those are the P waves. So this image shows seismograms from an earthquake in the same area as a later North Korean nuclear test. The height of the waves also indicates the strength of the explosion. In May 2009, North Korea tested another bomb, and based on that seismogram, that 2009 bomb was 5 times stronger than the one from 2006. So the earthquake monitoring network was set up not to study earthquakes, it was to see who's testing nuclear bombs. We can also use seismograms to investigate actions like coal mine collapse. In August 2007, a coal mine collapsed in Utah killed 6. The owner of the Crandall Canyon mine claimed that the collapse was because of a natural earthquake, that he wasn't at fault. However, mine collapses produce mainly compressional stress, just like explosions. The seismogram resulting from that event clearly showed lots of P waves, those compressional stresses, very few S waves. So after several days of challenging the seismograms, the owner then claimed that there must have been a natural buildup of methane which caused an explosion. The owner didn't know that the Lawrence Livermore Laboratory in California had been working on a new way of showing seismic data. This method also discriminates between explosions and implosions. Eventually, the owner confirmed that it was a mine collapse, but then claimed that the mine hadn't had any safety violations in the past. Well, it turned out that the mine did have dozens of citations in the previous year. Additionally, the cause of the collapse was a mining technique that is technically legal, but only with a special permit. They did not have the permit. So let's go back to that global network of seismic wave recording stations. Tuzo Wilson was the first to map out the recorded earthquakes. Rather than being evenly distributed, most earthquakes are concentrated into narrow zones, which is what was expected. What wasn't expected is that these narrow zones all match up with each other. Okay. So it was along these zones that Wilson hypothesized that major fault networks separate tectonic plates. In addition to the locations of quakes, he also mapped out the depths of the earthquake, and that information can help determine the specific type of tectonic boundaries. There are 3 main types of tectonic boundaries. At transform boundaries, plates move side by side. At convergent boundaries, they come together. At divergent boundaries, plates move away from each other. So divergent boundaries, as shown here, always have numerous and frequent eruptions and shallow earthquakes. The earthquakes are usually not very bad, and the eruptions are usually not very extreme, except where they're built up to the point where they have eruptions on islands such as Iceland. Most of the other eruptions along the Mid-Atlantic Ridge are rather slow, calm events. Now, most divergent boundaries start in oceanic crust, which is much thinner than continental crust and therefore easier to pull apart. But sometimes continents are torn apart. The former supercontinent Pangaea was split into the current continents, and Africa is currently developing a new divergent boundary. The East African Rift Valley can be seen as a north-south chain of lakes that formed after the stretching of land caused the elevation to drop. However, it's unknown whether that East African Rift Valley will continue and form a new continent. 1.1 billion years ago, a similar rift formed in North America, but for some unknown reason, it stopped and didn't tear the continent into pieces. Transform boundaries occur as short segments connecting divergent boundaries. There are 2 locations with long transform boundaries on land, Turkey and California. Both places are highly populated and experience frequent shallow earthquakes, just like divergent boundaries. But transform boundaries do not have volcanic activity associated with them. So unlike in the movies, a volcanic eruption cannot happen in Los Angeles. There are 3 types of convergent boundaries depending on what types of tectonic plates are approaching each other. If an oceanic and continental plate collide, the oceanic plate is pushed down or subducted. The oceanic plate is subducted because it's denser. As it is pushed down, the rocks begin to melt. And because magma is less dense than solid rock, the magma rises to the surface. The result is a chain called a continental volcanic arc. Also, notice that the oceanic crust moves from the surface to very deep within the Earth. Therefore, earthquakes at convergent boundaries can be either shallow or deep. And depending on the pattern of shallow and deep, that can tell you the direction in which the crusts are moving. If two oceanic plates come together, the older plate subducts. This is because that rock has had more time to cool and condense. In this situation, the volcanoes form underwater initially. The chain is then called a volcanic arc, and the Japanese islands are a good example of this. If two continental plates collide, both plates are much less dense than the underlying material, so neither subducts and you have no volcanic activity. However, you do have mountain building, which is going to include a lot of shallow earthquakes. So there's no volcanoes, but it's easily recognized by the large mountain range that's being formed. The overall speed of these plate movements is about the same as how fast your fingernails grow. It's a slow process. Long-term estimates for the speed of plate motion can be obtained from the pattern of magnetic striping on the seafloor, but that only gives us an average value over tens or hundreds of millions of years. Short-term data can be collected using satellites and ground-based lasers. I mentioned earlier that seismic waves tell us about the interior of the Earth. It's also the interior of the Earth that provides the energy to drive plate tectonics. The cycling of heat forces the flow of materials on the surface. So we've introduced cycles now within Earth sciences. Most of the cycles that environmental scientists deal with are closer to the surface. Perhaps the three most basic ones are listed here, but there are thousands of others. The key to studying any type of cycle is to first identify the reservoirs, and then to determine the way materials or energy flow between reservoirs. Unfortunately, this is often complicated by the fact that individual reservoirs can have their own cycles within them, and various cycles are going to interact. As an example, if we were studying the hydrologic cycle, we might identify the following 6 major reservoirs. Water moves by the processes of evaporation, precipitation, sublimation, and gravity. However, we could zoom in on just one of these. We can zoom in just on the oceans. This reservoir of water has an overall circulation pattern driven by changes in water temperature and salinity, primarily by water temperature and salinity. That's the thermohaline circulation. Most of the world's ocean moves along this pattern, the Great Ocean Conveyor Belt. Water near the surface is warmer, which causes it to be less dense. But after water has been on the surface for a while, evaporation causes the salinity to increase, thereby increasing density. It is this combination of changing temperature and changing salinity that also brings up nutrients from the seafloor and moves oxygen down toward the bottom. However, within the oceans, there are sub-reservoirs that only interact a little. There is another current, for example, called the Circumantarctic Current that only moves water around Antarctica because the water stays so cold it doesn't interact with other waters. There is also the changing influxes from land. If there is an increase in the amount of salt from rivers moving into oceans, that could cause water to become denser and sink. On the flip side, melting ice from Greenland could make water less saline and prevent water from descending in the North Atlantic Ocean. Now, why are these influences important? Well, if melting ice from Greenland prevents water from descending, the North Atlantic current, which is keeping Europe, especially Northern Europe, warm today, would be turned off. In other words, warming temperatures in Greenland could send Europe into an ice age. There are many types of cycles that also influence climate patterns. I've just picked the Milankovitch cycles here because these cycles go beyond the scope of just Earth. They deal mainly with the intensity of the seasons and the distribution of heat on the planet. In spite of the fact that these cycles, especially the one on the far right, eccentricity, correlate closely to some past ice ages, they do not change the total amount of energy reaching the Earth, just the distribution of heat and the intensity of seasons. However, the composition of the atmosphere does affect how much energy makes it to the surface. Additionally, the atmospheric currents determine the direction of the surface ocean currents and the movement of atmospheric moisture. And obviously these are just a couple examples of cycles that interact with the hydrologic cycle. Because this is a lecture on geology, I want to finish with one last cycle, the rock cycle. There are three basic types of rocks. Igneous rocks form from the cooling of magma or lava. As molten rocks cool, crystals grow in an interlocking framework. The rate of cooling determines the size of the crystals. If magma cools slowly, like it would deep underground, crystals would only start to grow in a few places. And this allows the crystals to grow slowly and become large before hitting an adjacent one. If lava cools quickly, like it would if you spilled it into the water, crystals would start to grow everywhere and quickly bump into other crystals. As a result, the crystal size can tell you the history of the igneous rocks formation. The type of crystals, the particular minerals that are in those crystals, that are in those rocks, will tell you the history of the magma that eventually formed that igneous rock. Sedimentary rocks are formed from pre-existing physical or chemical fragments of rocks and other materials. They are formed at or very near the surface. Therefore, these are the rocks that preserve the environmental condition of the Earth's surface. Sometimes this could be from fossils. I mean, if you find a mammoth tooth, the area probably wasn't a deep ocean region at that time. Sometimes the paleo-environmental data is from the chemistry of the rocks. For example, stable oxygen isotopes will record temperature. Sometimes the environmental conditions are from the types of rocks. If you find coal, the area was warm and swampy. If you find salt, the area had high rates of evaporation. Metamorphic rocks are created with any rock that is changed by heat, pressure, and some fluid. And that fluid is usually water. These altering agents allow ions to migrate and form new minerals without the material melting. The combination of materials, the new combination of minerals, I should say, tells the conditions of the metamorphic activity. So these are most useful in studying mountain building events and tectonic events. The particular minerals indicate the depth at which the rocks were buried and the amount of stress that was applied. Each of the three categories of rock can become any of the other three categories. Most people actually make the same mistake when drawing a rock cycle. It's easy to forget that a rock can become a new rock in that same category. For example, this image shows sedimentary rocks being broken down by weathering and the sediments being turned into new sedimentary rocks, which is good, but it doesn't show metamorphic rocks turning directly into new metamorphic rocks. So any of the types of rocks can become any of the types of rocks.